Okay, and when will be done now with this example on how to perform, how to set the different methods, how to put the residuals conditions, and how to perform a run. The next step will be to see how to simulate results, and we'll go over several other more complex examples to see how we can simulate different engineering applications using CFD. Okay. So we already introduced last time how to start to build our setup. To remind you, first we go through general, where we can determine if it's transient or steady. I will tell you what is the difference. If you select the steady option, then when you select calculation activities, they will not ask for a time step. However, if you click on transient, then you should specify what is the time step required, how many iterations should we do per time step, etc. Okay, so we'll take both cases. In case you have steady application, you just select steady, and here you can introduce if the gravity has an effect or not. You can include it. If you can neglect gravity, you can just disable this option. If gravity is important in your application, you just set it and you put the value of G. Okay. Now, concerning the models, last time we talked about the different models, and we have seen that depending on our applications, we have several options. So let's say if we have an application where energy is important, we should put it on. In case we want to generate particles, we have several options. We have the multi-phase, we have the species, we have the discrete phase. So today, for example, we'll talk about how to generate particles using discrete phase mode. And through the lab, we'll go over different other strategies. Now, next, we determine boundary conditions. So when we enter boundary conditions, we set the conditions on the different parts of our domain. After this, now we were talking about the methods used. These methods, you'll see their details in the course material. So we'll understand more what do we mean by pressure velocity coupling, what do we mean by, for example, for pressure, the Presto scheme, etc. Now, I will just give you some recommended schemes that can be used to simulate flows. So for example, for pressure velocity coupling, a common scheme that can be used is simple. For pressure, we can use Presto. For momentum, for other momentum, turbulent kinetic energy, and turbulent dissipation rate, it's always better to select the second order scheme because it will, the first order will be less accurate than second order. And we'll talk in detail in the theory together about this. So this is for our methods, and energy also we set as second order. Now, let us move to controls. For the controls, you have what we call under relaxation factors. What do we mean by under relaxation factors? Also, we'll tackle this into the course material, but just to introduce you to the concept, the idea is that using CFD, what you will do, you will solve for several equations. You will solve for continuity, for Navier-Stokes, for energy equations, okay? And you transform your differential equation to numerical ones, and you write the equation equal to 0, okay? Now, what will happen is that, let's say, when you arrange your terms like this, you have at the end, you should have, let's say here 0, and you update your values. So, for example, you update at each iteration your temperature, at iteration I, your velocity, etc. Now, sometimes if the change of value from one iteration to the other is really big, this might lead to divergence of your solution. Your solution will not be able to reach the converged real solution. Okay, so this is why we say, to avoid this sudden change in values, which can cause divergence, we use what we call under relaxation factors. What we mean by this? So for example, if in iteration, at a certain iteration, the temperature value was 21 degrees, okay? And at next iteration, it is 22 degrees, for example. So instead of jumping directly 1 degree, I will say, let's say if delta T is equal to 1, I will not take the whole change. I will take, for example, 50% of the change. So let's say I will update T to 21.5. So this is a relaxation, an under relaxation of 50%, because I just updated the value by 50% of the difference. So in this, yeah.
سوري قطشتك، بس عم تحكيني ريتا ابو خليل ما عم فيها تفوت على الصف، لازم انت تفوتيها او شيء هيك، عم بحطوا لها انت in another meeting.
ريتا لا ريتا تفوت على اللينك on مودل on e-learning سوري. اوكي حطيته هيدا، حطيت لكم اياه today. It's an updated link لانه هيداك expired, the other link expired.
اوكي thank you.
Okay, so in this way we can smoothen, if you want, the variation of our variables, and then we will reach the solution in a smoother converged way. It's true that it will take more time because we are not updating in a fast way, but sometimes it's necessary to do it. So in general, these under relaxation factors come with experience. You cannot directly know what should I take these factors. You should do several runs, you should try values, and here I will give you, according to experience, what are the under relaxation factors we can use. And in case sometimes you faced convergence problems, one of the strategies to reach convergence is to reduce the values of under relaxation factors. Okay, so when you say under relaxation factor is 1, this means that you are taking the whole variation of your variable. However, when you put it between 0 and 1, then you are taking a smaller percentage of the variation. Okay, now I will give you the recommended values for under relaxation factors that I used to work with. Now, as you can see, by default already, you have under relaxation factors in your already implemented in your setup, but we can modify them. In general, pressure is a critical variable. This is why the under relaxation factor is much smaller than 1. This means I will take 30% of the update in my value. Now, for density, I recommend to use 0.7, so 70%. Okay, let me check. It's not taking the, okay, it's not taking the comma. I don't know why. Let me take this. So for density, I recommend 0.7. For body forces also, I recommend 0.7. For momentum is in the majority of fluid application a challenging equation to converge, and you will see this by observing your residuals. In a while, we'll talk about residuals. What do we mean by residuals of equations? And we'll see together that momentum is not do not converge in an easy way. This is why we can recommend a value of 0.3 for momentum equations. Now, when you select the K, if you remember, for turbulence model last time, we selected the K epsilon model. The K epsilon model is a model introducing 2 variables to account for turbulence effects, which is K, the turbulent kinetic energy, and epsilon, the turbulent dissipation rate. So as I told you, whenever you implement 2 new variables, you will have 2 new equations to solve for these variables, and then you should define an under relaxation factors for them. Good values are 0.8, 0.8, so it's fine, you can keep them like this. Now for the turbulent viscosity, I also recommend this value, 0.8. Energy is one of the easiest variable in convergence. So you will see that when you do your run, the temperature graph of residuals will be the faster one to converge. So in general, energy is not challenging to converge. It's one of the easiest variable to converge. This is why 1 is good, and 0.9 and it would be enough. So you can under relax to 0.9. Now, if you implement discrete phase, so if you inject particles, you can do a certain under relaxation factor. So let us keep it by default 0.5. And in case you observe divergence in your discrete phase modeling, you can reduce more this factor. So this was about the under relaxation factors. In the course material, we'll talk more about this, how it's implemented into our equations. Okay. Now, concerning the monitors, whenever we click on monitors, we can mainly, if you want, specify, for example, residuals. So here you can select for residuals. And what is residuals? We already talked about several equations that ANSYS Fluent is solving. Okay. So what we will do then is we will write the equations. So ANSYS will write the numerical equations and set them. So he will take all terms to one side and you will have equal to 0. Okay. And now what will happen is that in reality, numerically, we'll not be able to reach 0 exactly, but we will approach from 0. Okay. So you can consider, for example, that convergence is reached when I reach for all my equation at least 0. For example, 0.001. Then we say that the residuals are 10 minus 3 in this case. So when all equations, if you want, drop below, so the equal part will drop below 0.001, your software will stop and will tell you that calculation is complete. Now, in general, for residuals, okay, we recommend values of, for example, 10 minus 4, 10 minus 5 if possible. And depending on applications, we can allow for larger residuals. So this depends on the application. By default in ANSYS Fluent, you have the residuals that are set to 0.001. Now, please, a very important concept is to normalize residuals. Why it's much more accurate to say I will normalize residuals instead of talking about absolute values. I will give you an example on this. Because sometimes, for example, if the range of temperatures in your space, okay, is between, let's say, 20 to 30 degrees, okay, then one degree of difference is considerable, okay. However, if the range of temperature in your space is between, let's say you are considering a combustion process and you have very large temperatures, so let's say up to 1000 degrees, for example, then 1 degree error is fine, okay. So when you normalize, you divide the, if you want, the relative error, the error you get in temperature, let's say, by a certain reference value for your temperature, for your application. So this is why it's interesting to normalize the residuals, because the same value of residual can be neglected for some applications while it's significant for other applications. So normalized residuals are much more representative of your problem. Okay, so always select normalized residual values, and you can take the default values of ANSYS, which are 10 minus 3, or if you want to have more higher accuracy, you can impose what you want. As you can see, by default, the energy in ANSYS is characterized directly by a more constrained residual 10 minus 6. Why? Because already, as I told you, energy is the easiest one to converge. So 10 minus 3 will reach it in a very simple, in a very fast way. So to have more accuracy, we go up to 10 minus 6 for energy. For other variables, you can change if you want, depending on your applications, the residuals. Higher accuracy needed will require smaller residuals. So you can set, so for example, all your residuals, let's say, to 10 minus 5, 10 minus 6. And anyway, you can stop at any time your simulation and see your results. So even if you didn't reach these values that you set initially, 10 minus 5, you can say, for example, when you reach 10 minus 4 and you obtain a physical solution that seems logical, you can stop then. Okay. And as I told you, the validation process will always help you to know to what extent I can consider that my solution is convergence. So when you build a CFD model and you compare it with experimental data, then you can set what are the good conditions to give me converged results. And when you set your methods and you set your numbers, then you can use the model you built to simulate new parameters, to conduct a parametric study, etc. Okay. So this is concerning the residuals. Now, for initialization procedure, what we mean by initialization procedure is to initialize values. So, for example, for temperature, let's say in a ventilated space, I will not start from 0 degrees. I will start from a common value, let's say, for example, 24 degrees. Okay, so this will, if you want, by starting with a good initial guess, then I can converge in a faster way. Okay, now we have several types of initialization. We'll talk about the difference. You can use the standard one. When you use standard initialization by default, then you will start from constant values, and these values you should specify them here. So, for example, we talked about absolute frame, and you can say for velocity, for pressure, I want to start from atmospheric pressure. For velocity field, I want to start, for example, you will have an idea, let's say, about what is the range of velocities in your indoor environment. So you can set such velocities. For temperature, similarly, for example, you can set it as, here it's 300 Kelvin, which correspond to 27 degrees. So you can put your initial values as you like. Now, what about hybrid initialization? It will consist, it's a little bit more complex, okay? It consists on solving a certain number of iteration of a simplified equation system, and thereby you will get usually a better guess for the flow variables. So these equations are implemented in ANSYS Fluent. And for example, for the particular case of pressure field, it will be based on solving a Laplace equation to determine what are the pressure and velocity parameters. Standard initialization works in general well, so you can keep it standard, but for more complex scenarios, you can go to hybrid initialization. Okay, so this is about the initial values you will start from. Now, concerning your calculation activities. So first, you have to, sometimes if you want to save your iterations, so you can go back to previous iterations and see with iteration how you have variation of your variables. You can tell the computer, no, do autosave each, for example, each 1000 iteration. Okay, because if you want to save each iteration, this will take more time for the simulation. So you can select a certain number of iterations, then when it completes, let's say 1000 iterations, it will stop, it will save, and then will continue. Okay, so this is about this. Now, concerning the running procedure, when you click on run calculation, you can determine what is the maximum number of iteration you want to do. So for example, let's say you want to leave your computer, and then after and you want your simulation to continue, to not stop before a certain number. Your calculation will stop in two cases. If you reach convergence, this is the case when you reach the residuals you specified, or it will stop when you reach the maximum number of iteration you specify here. In general, put a large number so that your computer will not stop before convergence. And in this way, if you want to leave it and then come back, it will continue to simulate until reaching convergence. Okay, so for example, 100,000 iterations will require a lot of time. So you can put this in a way to avoid your computer stopping at a certain level. Okay, now, as I told you, in case you selected transient, then you will have here in the run calculation some modifications. Let us see how. So I will go back to general. Hello, 1 minute, it's taking some time. So in general, you have the option to select for steady or transient, okay? If you select a transient application, and then you go back to run calculation, you will have a small modification, okay? We'll see here that now you have to determine what is the time step size. This means that what is the interval of time of updating, and you will solve for t equals 0 second, 1 second, 2 seconds, then the time step is 1. If you want to have a smaller time step size, you can select, for example, here, each 0.1 second I want to perform, let's say, a certain a new iteration, okay? And the selection of time step, also will discuss this into the course material, how to select a time step that will allow you to have convergence, okay? The time step is very critical to have convergent results. So sometimes if you select a very large time step, you will have divergence. And also, maybe if you get it very small, it's not very good. So we'll see how to optimize this time step for certain problems. And in addition, here you can see you have an additional parameter, which is what is the maximum iterations we want to do per time step. What do we mean by this? So whenever you specify a certain time step, in order to get a more accurate value, you do within this time step several iterations before updating your values. So here you can do several iterations in one time step. So you can specify, let's say I want to do 10 iteration before updating the values for next time step, okay? And then after specifying these criteria, also you should select what is the total number of time steps I want to solve for. So let's say you want to do simulation over, let's say 2 minutes, okay? Then you determine how many time step should I have in 2 minutes, you enter it here, okay? So let us put anything now. So let's say I want to do 1000 time steps. This means that I am solving for 100 seconds, okay, because each time step is 0.1. So I just multiply 0.1 by the number of time steps. I get that in total, I am simulating my system over 100 seconds. Now, whenever you do this, and whenever you are done with this, you are ready to start your simulation. So you can just press calculate. Okay, and you will see that when you press calculate, you will observe now here in your window a graph with residuals that we talked about. Okay, they will start by large values, and with solution they will start to decrease. Okay, so now yeah, just 1 minute they will appear. And we can see if they have a convergent behavior or not. We should wait some time, okay, because sometimes at the initial state that the residuals can go up, but they will go after down. So we should not directly stop the simulation. We should give it some time, and then we'll see how the residual pattern is. So the expected pattern will be like this. You will have a graph. You have on an axis here, you will have residuals, and you have residuals for your different variables. So for your velocity, for your temperature, etc. And here you have the axis of iterations. Okay, you will start to see graphs doing the, and sometimes you can observe an increased pattern first, and then it will be reduced. So you expect that at the end you should have a decreasing profile, and then your system will stop whenever all residuals drop below the selected value. If you selected the same value for all, let's say 10 minus 6 for all, they should all drop below 10 minus 6. Sometimes, as we said before, some variables are much easier to converge than others. So you can set, let's say, for temperature 10 minus 6, for momentum 10 minus 3, etc. So when all your variables drop, residuals values drop below the critical value you selected, your simulation will stop automatically, and it will tell you that you have reached convergence, and then you can explore your results. Okay. Now you should wait. Okay, you should observe your residuals. You can interrupt at any time your calculation. So I don't know what is the issue. Maybe it's taking some time to calculate. It's fine. So what we will do then, we will observe residuals, and whenever we see that we started to have decreasing residuals, we can check the state of our results with time. Okay. So here, okay, so in this case, look, maybe because it's transient, it's taking some extra time. Let me put it steady now to have a smoother procedure. Okay, and then I will put also DPM off, because this might take time to simulate. 1 second, and then we'll do the run again. Okay, so let me try to run again. Okay, so as I told you, you can stop anytime, anytime during the simulation process. You can you can click stop calculation, and then you can check your results to see if everything is going well or not. And then you can follow this your simulation at different steps, at different number of iterations, to see how your solution is how it's improving with time, how with a higher number of iterations you are getting more accurate results. And when your residuals become stable relatively, then your solution will not vary anymore, and you can consider that you reached convergence. Now, in case your residuals are diverging, then what you should do is to, if you want, try to, for example, one strategy is to reduce the under relaxation factor. Another strategy is to go again to your mesh and check if you can enhance its quality. In the meshing videos, I gave you several hints to enhance the quality of your mesh. So you can try to maybe reduce the skewness, do more face sizing, reduce the size of your elements, increase the number of elements in your domain. So by using smaller elements, this can be more helpful in order to avoid divergence issues. So you have several techniques, and you will gain these skills as you go with your project. And you need to experiment this, to try, do several trials to see what is the best mesh to use. And we do sometimes we do what is called grid independence for mesh. What do we mean by this? Sometimes you obtain a convergence, okay, your solution is converged, but how to determine if really I am close to the final solution to a big amount or not? What we can do then, we do what is called grid independence test. So we change, we try to increase the number of elements, and to see for within our domain, to see if this will affect results. And we keep increasing the number of elements until variation of results. So let's say you can explore at certain locations, what is the temperature for mesh 1, what is the temperature at this location, velocity, etc. for mesh 2. So you take several grids and you see how your predictions are varying. When you see that for 2 consecutive meshes, the difference is not very high, you can say, then it's fine. No need to increase the number of elements anymore, because if I'm increasing the number of elements, I'm not getting more accurate results. So this mesh is fine for me. Okay, this can help you to select the appropriate mesh. Now you can see here, as I told you, a graph of residuals with iterations. So you have different graphs. You have, each one is for a certain variable. The white one is for continuity. You have the red, green, and blue one for the component of velocity. So here you can observe velocity variation in X, Y, and Z. You have the blue line is for energy, and you have for K epsilon pink and yellow colors. Okay, so we can see how the residuals are evolving. Depending on the speed of your computer, if it's a and depending on also if you are conducting in series or in parallel, so this depends on the number of processors of your computer, the time for each iteration will change. Okay, and you should observe the profile of your residual. So as I told you, for certain variables, you will start to observe first an increase in residual, followed by a decrease. Or sometimes if the solution is divergent, maybe you will have direct increase and they will never be reduced. Then you can directly, after let's say you wait some maybe 100 iterations, if the increasing profile is continuing, then you stop and you try to, as I told you, you try to reduce your anti-relaxation factors, you try to change your mesh, to improve your mesh quality in order to avoid any divergence. And sometimes for study applications, one good strategy to converge is to set it first as transient. Even if you have a study application, if you apply transient mode, the transient mode will lead to a smoother, if you want, variation of your solution. And when after reaching convergence, you can switch back to study. This is a technique widely used in order to ensure convergence also. So you have several hints that you can use to have convergence. So here you can start to observe your residuals. You can see that nearly the initial value of residuals is nearly 1. And you are very far now from your desired values, which are, let's say, 10 minus 3 or 10 minus 4, minus 5, minus 6. You need time to reach these values.
دكتور
Yeah.
بس أنا طريقة متأخر شوي يعني فقط
Yes.
شي ربع ساعة.
No
شو
problem.
قصدنا بكلمة residuals فعليا؟
Yes. Yeah. What I mean by residuals, you have ANSYS Fluent is solving for your equations. And we already talked about continuity equation. So whenever you write the continuity equation, you can take all terms to one side, so the other side will be 0. Okay, so the idea in Fluent, you transform the differential equations into numerical ones, and you take all terms to one side. This should be equal to 0. Now, when you do the calculations, the simulation, you will not exactly reach 0. Okay, and if you reach 0, this means that you reached the accurate value, the accurate solution. Okay, now the closer this number to 0, then you are closer to the real solution. So what I mean by residual is the number you obtain here. So when you solve, for example, as a start, you will start maybe by getting 1. And as you do iterations, you will be closer to 0. For residual is a number that you can allow. So you say, for example, I want to reach for the temperature equation, for example, when it will reach 10 minus 6, for the other side here, I consider that it's very close to 0. I consider that temperature is converged. Okay, and you can select your residuals for all variables. Now, with experience, energy is easier to converge than other variables. This is why I set it as 10 minus 6. Momentum or continuity is one of the more challenging variables. So as you can see here, continuity is in white. You see that the reduction of white curve is very, it's done at a very slow rate. However, for energy here, it's not, it's going better than continuity, but still it's not very fast. It depends on the turbulence level also. And the turbulence level will affect also the energy performance and the heat fluxes you have and type of heat transfer processes. More they are complex, this will require more time for more iterations for energy to converge. But in general, energy is easier to converge than continuity. And you can observe this for a large number of iterations. So here, as you can see, we can explore how residuals are varying. It's a little bit slow here, but you can, I told you, depending on your computer you can have an accelerated rate for iterations. So what you will do at any time, you can stop your simulation by just clicking on stop here. Let's say I want to stop to see what happened until now. Of course, here I just did 11 iterations and I cannot explore anything. But the idea is that you can stop whenever you want and you can check at this stage what is your results. Okay, so we'll see how. So when you click on stop, your run will end at this stage and resume calculation whenever you want. So now we can go to graphs. Okay, you can try to see what is the state of your solution. You can observe, let's say, temperature field, velocity field, to see if what is the stage we reached in our solution. Yeah, now in a while we'll see how. In the contours, you can explore for your if you want graphs for your different variables. You can see your temperature graphs, your velocity contours, explore so until now able to do your geometry. Okay, then you can mesh it using several techniques. In the setup, you will implement what methods of solution you want to use, what are your boundary conditions. In addition, you can select if it's a transient or steady application. You can consider what is the type of methods I want to use. It is a second order scheme, it's a first order scheme, etc. You can also determine what accuracy I want to reach, what are the residuals that are allowed for the different variables of continuity, velocity, temperature, turbulent parameters as k and epsilon, etc. And you will run your simulation. You should wait for a number of iterations that is high enough to have decrease of your residuals. Okay, and then whenever you have reached a nearly convergent state of your residuals, you can stop from time to time. Even if you didn't reach the residuals you selected, like 10 minus 6, for example, if you reach 10 minus 4, you can say, let me check if these residuals will give me a good result. So I can stop if you want before the criteria I put for convergence. I explore my results. I see if I see if they are physical. And also one very important parameters, as we mentioned, is the validation. The experimental validation or validation with literature data. What do we mean by this? You can go to literature, to previous work done. You can try to simulate same conditions, and you draw a domain that is similar to one that is already solved experimentally, and you compare results. Okay, and once you see that the features you are using for your CFD models, with what we mean by these features, the methods you are using, the residuals you set, etc., if they are allowing the mesh quality you reached, if they allow you to really predict experimental data, then you say, my model is working well, let me now use it to conduct a parametric study. Okay, and then once you have a converged solution, you will see together how you can express your results and how to have physical interpretation of these results. Okay, so it seems that it's not more. We can stop for today until here. Okay, and hopefully we can next time, after you try to do at least a simulation with an enough number of iterations, we'll be able to move to how to explore results, and also we'll see how to if you want inject particles or see how particles can spread within a space, to study, for example, contamination effects, or to study, let's say, concentration of CO2 in a space, what is the level of ppm. So you can check, then let's say you have actually recommendations for CO2 levels. You can check which ventilation system can allow us to reach the recommended CO2 levels in the room, etc. And you have a lot of applications that can be used just for ventilation systems. When we'll be done with this, we'll consider more other applications. Now, concerning the projects, okay, I will give you several projects, and you can select one of these ideas, or also you can suggest your own idea. So if you have an idea in mind and you want to try to do it as project, then you tell me what is your idea, and I will tell you if it's feasible or not. Okay. Any question on what we did today? Okay, so we continue next time. Thank you. Dear students, ما بعرف شو صار بأنسس علق. So let us continue next time. Okay. Dear students,
ولا الشمالية أصلا شوية